Okay, so here's the library we're going to look at. So this structures library is a open source project of mine, and it is built up in a very similar way to what we've been doing so far. It has all of the really major type classes from functional programming and Scala. A lot of the things that are in Scala Z, or at least some of the simpler things that are in Scala Z. Without any of like the data structures or concurrency abstractions or XML parsers or any of kind of the extra stuff. So rather than derive everything from scratch like we've been doing so far, let's just take a look around at how functor, applicative, and monoid are defined in this project, and then we will move into those additional type classes. So this is a regular SBT build. There's a bunch of different projects. If we run tests, you'll see that this is using like a similar testing structure to what we've been working with so far. Here there were, looks like about 99 different tests that were run. You can see things like, for instance, a bunch of tests for the option data type, a bunch of different laws to make sure it complies with all those laws, a bunch of things for the list data type, etc. If we look at the project list again, we'll see that there is like a core project. It's split up into a core project for the JVM and a core project for JavaScript. Structures does build on, or does build for Scala.js, thanks to Matt. You can use all of these abstractions in the browser. There's also like a laws project, which defines all of the laws for the type classes in a very general way, the same way we were defining them so far. And then there's a project called Discipline, which takes the laws and binds them to a specific testing framework. So like that's where we can start writing, for instance, Scala test-based unit tests that verify that like option adheres to all the laws. So let's take a look at Functor and see what it looks like in this code base. So here's our Functor type class. You can see it's in the core subproject. It's in the shared subdirectory of that, and then source main Scala. This shared JVS JVM directory structure is from the Scala.js plugin. It's what lets us have like JavaScript specific code versus JVM specific code versus Scala source files that are shared across both builds. But otherwise, underneath shared, it looks pretty standard, source main Scala. And in the main package structures, we have this functor type. You can see it's annotated with that type class, just like we were doing recently. Unlike what we saw a couple weeks ago. Yeah, go ahead.
Mike?
Yeah.
Can you repeat what you were saying about the what you got from like the structures again? The shared versus.
Yeah, this is this shared directory versus JVM versus JS. This comes from Scala.js. Specifically, like in this project, in our build.scala, down here where we define the core project, we have this cross project thing. And this is basically, this cross project def here comes from the Scala.js build support for SBT. And it lets us build this core project for both JavaScript runtimes as well as, JVM runtimes. So it sets up our source folders such that we've got like 3 roots. We've got the JS root, the JVM root, and the shared root. When we're compiling like a jar for the core project, it's going to use source files from shared as well as source files from JVM, where the JVM directory is going to override the stuff in shared if you've got like a name conflict. And if we're doing stuff for the browser, it's going to use source files from JS and then shared. In this case, you can see both these JS and JVM directories are empty. We only have a shared directory. Okay. Yeah, so back to Functor. We have, this looks a little bit more complicated than what we saw when we wrote this ourselves. We extend any, which might seem redundant in Scala, but this is actually, this is not redundant. This is actually changes the way this trait may be compiled. So specifically, this turns Functor into what's called a universal trait. And universal traits cannot have any state whatsoever. It's like no vowels. Universal traits are the only type of traits that may be mixed into value classes. So we want to be able to have Functor be mixed into value classes, so we extend any. Extending any is sort of similar to like a Java interface definition, except that we can have concrete methods, right? So like our void function down here looks the same as the void function we defined in our first lecture. We just implement it in terms of map. We clearly can't define like a concrete method in a Java interface, and yet we can in a universal trait. The other difference here is that our functor was rooted, or was the root of our like inheritance tree. Here we've got a parent type of exponential, and we'll talk about that in a number of weeks from now. There is a tentative agenda listed on the wiki page I posted today, which has at least what I currently think is the order of topics that we'll tackle this stuff. So we'll come back and look at exponential in the future. Anyway, here's the rest of our functor trait. We have void, lift, and as, just like we defined ourselves. We have this one function here called zipWidth, and zipWidth is kind of interesting. It says, given an FA and a function from A to B, give me back a pair A and B wrapped in F. So basically what it's doing is saying, let's remember the input value, the initial value A. We'll put that input value into the output first element of the tuple. And in the second element of the tuple, we will have the result of applying F with this value A. So for anyone that knows like Scala Z very well, this is actually called F product in Scala Z. It's also called F product in Haskell. And otherwise, this looks very similar to what we saw before. Again, there's some extra type classes here, like this contravariant stuff, which we won't worry about right now. But like our compose, for instance, looks very similar. It happens to have the double mapping logic, factored out into a trait in the companion object. But otherwise, this is feature-wise, matches up with what we did. Now, our companion object only has this composite trait, and it ends up having this contravariant composite trait. Again, we'll talk about that later. It doesn't have all of our instances for things like lists and maps and so on. And it turns out that wasn't a very repeatable, or at least it wasn't a very succinct way to define the instances for all those data types. We were defining list across all, we did list in Functor, applicative, and monad, and as we get into a large set of type classes, that'd be a lot of repetition in each one of those to define list there. So the way this code is structured is that there's a sub package called std. This is short for like standard library, and it's where all of the instances of these type classes are defined for the various standard library types. So in our list file here, you can see in the standard library package, we have this trait called list. And it's got a series of methods here. We have one method that says we can generate an equals instance for a list. This looks very similar to what we used in previous talks. And then we have a more complicated definition. We'll see like monad combine, we'll see traverse in subsequent weeks. But nonetheless, you can see like pure and flat map as the first two methods here. You can probably guess that like Monoid combine is going to derive from Monoid eventually. And this is this same definition for pure and flat map that we used last week. There's also this object list extends list. So now, like if we wanted to use the instances for list, we would just be able to type like import structures.std.list._. And this is very similar to like the Scala Z7 import structure. And here's our definition for options. Again, there's multiple methods inside a trait, and then a companion object that extends that trait. These are all lowercase, by the way, because they're kind of simulating packages in their usage. We want people to say like import std.option._. And there's a bunch of others like things for like integers, bytes, shorts, long strings, ethers, maps, so on. So this is the general structure. Let's see what it's like to use it. Oops. All right. So I'm going to go into the core JVM project and open a console. And you see I've got SBT configured to do 3 imports right off the bat every time we open a console. So it's going to import everything in the structures package. It's going to import the standard package. And then it's going to import all of the extension methods for all the data types. So for example, if we were to look back at Functor, remember we have the as method on Functor, which lets us just replace the a with some other value b. And we also have the void method, which just let us turn everything to units. So what we should be able to do at this point is just say like list123.as0. Or we could say like list123.void. Right? And that's because the import for structures.ops._, that's going to give us all the extension methods, assuming we've got like an implicit functor of list available. And we're going to get the implicit functor of list from this import here. So this is very similar to the Scala Z7 import structure. Both of these two objects that we're importing things from are like these mass import objects. We're getting all of the standard instances, right? So not only list, but we also get like map, for instance. So we had like map 1 to the string 1, 2 to the string 2. Actually, this isn't going to work. Let's use option, for instance. Right, we can turn an option int into an option unit via the void method. Right, so we're getting all of the predefined type class instances from this. We're getting all of the syntax from that. So there's really no magic to how that's working. The standard object is just coming from the package object in the standard package, right? We have a package object standard extends, and then it pulls in all of those individual traits. That's why like list and option we saw were traits as well as objects, so that we could do this import here. It's also why, like if you look in list, all of the methods are prefixed with list, right? Because we know we're going to mix this trait in with all of the other traits in this package. We want to make sure all the names are unique. And the ops object, you can see, is pretty big. The ops object is just pulling in all of the enrichment classes generated by Simulacrum. So Simulacrum is what gave us the ability to do like .void on a value rather than having to go and look up the type class directly and then call void passing the value we're trying to call it on. And here we just kind of bring all of those together under one import. So anyway, that's what lets us do things like this. All right, so let's look at our first type class for the day. And let's start it with a quick demo. Let's do this here. We're going to start with like the list 1, 2, 3. And the first thing we're going to look at is semigroups. It's the ability to have an associative binary operation, or an associative method that takes two values of the same type and returns a value of that type. So we've talked about this a bunch, and I think we even showed it last week, although we didn't talk about it much. And here we can see the first execution of a semigroup. We're using like the semigroup for lists that is list concatenation. So this is the same as doing like list 1, 2, 3 plus list 4, 5, 6. We can also do, or we can also use the semigroup for, let's say, integers directly. Here, of course, at least with a couple tries, we can try to figure out what it's doing. It looks like integer addition, and you can see that all the examples we throw at it, it appears to be addition. Let's try option. So in the option case, this is a little bit more interesting, I think. We can't do the list case, right, of just concatenating two lists together, because an option only contains one value, of course. But you can see like we're effectively summing the inside value. So when we get a 1 plus an optional 1 plus an optional 2, we get sum 3 back. If we were to put a none on either side, we get back the opposite side untouched. And it really is summing this inside value right there. We'll get 4, we'll get 5. And let's do one other example before we look at how this is implemented. Let's do maps. So let's say we've got a map that maps the string even to the set 2, 4, 6, 8. That's our first map, and we will combine that with the map even. We'll say the set 10, 12. And we'll also have odd map to the set 1, 3, 5. In this case, we got a compile error, and that's because we don't actually have support for sets in structures at this point. If we were to replace these with lists, you'll see what the answer will be. We get back a single map where even is mapped to the list 2, 4, 6, 8, 10, 12. And odd is mapped to the list 1, 3, 5. So this is very interesting, I think, because we basically unioned the two maps. But when we had a key collision, both the left and the right map contained the same key even, their values were unioned or were combined together. Right? So here we had 2, 4, 6, 8, and here we had 10, 12, and of course we got one big list there. And this works like arbitrarily deeply, so we could have like maps of lists of maps, and this will all work just fine. So let's take a look at how this is implemented. Here's our definition for semigroup. You can see it's much simpler than anything we've written so far. A semigroup is a type class that abstracts over a proper type. So unlike Functor, unlike applicative, unlike Monoid, those all worked over type constructors. With semigroups, they all work over just a direct proper type. And we saw that, right? We were working with like a list of int, we were working with an integer, we were working with a map of something. And it's just going to define a single abstract operation called combine that takes two values of type A. Just so happens that like the second value y is a by name parameter. It doesn't have to be. We do that because some semigroups can evaluate can evaluate combine without actually evaluating the y parameter. but it's not really essential to the definition. We also have this annotation here on the method. This is a simulacrum annotation where we say, when you go to generate the operator for this method, instead of using the word combine, use this pipe plus pipe name. This is just pretty standard, both in Scala Z and in Haskell. So that's our full definition of semigroup. Now we'll have to look at a law for that, and I'll look at that in a second. You can see that the companion object just has a convenience constructor, that if you just give it the combine function, it'll just implement it for you, give you back a semigroup, and just delegate to your combine function. And we'll use the instance method a bunch to define our semigroup instances. That's why I bring it up. All right, but let's go look at our laws. Here are the laws for semigroup. This is going to use the same syntax that we were using last week for like the Monoid laws. So we have a trait that defines all the laws. We capture the type that we're going to define the laws over as a parameter to that trait. We then have an instance of semigroup for that parameter. Here is an implicit val. And we import our operations off that so we can use the extension methods directly. And so the only law says, given three values of type A, x, y, and z, combining x and y and then combining z must be equal to x combined with the results of combining y and z. Right, so this is just an associativity property. Note that we're not requiring this method to be commutative, right? So we're not saying that like x, that this particular arrangement, x plus y plus z, has to be equal to, for example, like y plus z plus x. Oh my. Right, we are not claiming this property. This would be a much stronger property than what a semigroup defines. So all we're doing is saying is if you are running them all in the same order, you can put the parentheses anywhere and you'll get the right answer or the same answer. All right, so let's look at our next type class, and then we're going to come back around and look at instances for both of those, both semigroup and monoids together. Here's our definition of monoid. So a monoid is very much like a semigroup in that it's defined over a proper type. In fact, we're going to extend semigroup, and we're going to add one method to it. Here we're calling it empty. And empty takes no parameters and just returns you a value of type A. So let's look at monoid laws. Here we have two laws, and you can see monoid laws extends the semigroup laws, so we're still going to require that our combine operation is associative. But now we're going to require, we have two identity laws. We have a left identity and a right identity law. And these are going to be very similar to like the monad left identity and right identity laws. In fact, there's a correspondence between them, but that's out of scope for today. And so the idea here is just that x combined with the empty value must give us back x. That's our right identity law. And our left identity law is saying the empty value combined with x must give us back x. And looking at the instances we saw at the REPL, like we saw integer addition as a semigroup or as a monoid, our operation itself, our combine operation, was just regular addition, and our empty value was some integer such that that integer plus some other value, or sorry, any value x plus some integer must be x. Of course, with addition, that's 0. In fact, if we look at any vals, and we look at like the definition of the int monoid, you can see that we start with the value 0, and we define combine as just addition. Byte, short, and long all are the same. You can see we have a monoid for string. String, we start with the empty string and just define our combine operation as string addition or string concatenation. And if we look at some more interesting ones, it's a little hard to see here, but the list monoid is basically defining the empty value as nil and the combine operation as plus plus, list concatenation. And then we get to one of the more interesting ones, which is the monoid definition. So we want to define a monoid for an optional value a. And we saw the way this behaved, right? We saw that like when we took sum1 and added none to it, we got sum1 as output. And we saw that we had like sum1 combined with sum2, we got sum3 as output. So it was actually like combining the inside value. So let's look at how this is implemented. You can see that we use monoid.instance and we pass the 0 value for our monoid. And here our 0 value is none. And that makes sense because, like I said, we saw that sum1 plus none equaled sum1. So our starting value, our 0 value, is going to be none. Then to combine two option A's, we've got an x and a y. They're both an option A. To combine them, here we're doing it with folds, but perhaps it's easier to see if we rewrite this to use a pattern match. So we can write out our cases pretty directly. We'll start with a case where we get two nones. We can just return none. Our next case is that we get some x, and we get a none on the y side, in which case we want to return some x. Our third case, we'll have a none on the x side, and we'll have a sum on the y side. We're going to return some y. And so far, these all just follow from the fact that we took none as our starting point. We said anything plus none must be that anything, right? So these three cases all follow directly from the choice of none as our empty value. So then we have to handle this case, where we get two sums defined. And we could try to say, let's just like cheat and try to use plus. But this isn't going to compile. And the reason it doesn't compile is because we've defined this option monoid, we've defined parametrically over any value of type A. And so values of type A don't have a plus method. But we can add this restriction to say that the values of type A have to have a semigroup because we need to be able to combine two A's into one A. And if we do that, then we can use the combine operator here instead of the just regular like plus method or plus plus method. So the interesting thing I think about this definition of monoid for option is it's one of the first examples we've seen where we need, in order to define one of these type class instances, we need to use a different type class instance for one of the type parameters. So one of the questions people have when they're first working with these structures is like, what's the point in pulling out a definition for semigroup or a definition for functor? Like, why are we abstracting this thing? And this is one of the first cases I think you'll see that answers that question with an example. right? So without this definition for semigroup, we'd have no way to abstract over the notion of adding two things together. Now, of course, we don't need a semigroup to do that. We could have written it, for example, we could have written this just as a regular def, and you could have defined like a parameter to this called like add, which takes two A's and returns an A. In which case, we could implement our sum case down here as add xx and yy. The downside of a definition like this is that you can't actually invoke option monoid now implicitly, which means like you can't just get a free monoid option A instance created for you. We can certainly keep the implicit keyword here, but with this parameter here being non-implicit, the compiler's never going to be able to call this. We could try to add the implicit keyword here, but now we're asking people that use this to make a function 2 available implicitly out in implicit scope. And it's a bit of a lie, because in order to do some of the more complex things we're going to do, we want to make sure our monoid instance adheres to the laws. And this particular definition would not be law-abiding unless our add function passed here is associative, right? Because we're returning a monoid. So by returning a monoid, we're claiming that this monoid instance we're returning is associative, as well as having the left identity and right identity laws. And we certainly pass left identity and right identity. We can see that in these three cases. So our, or at least we can kind of suspect this, that our proof that the monoid for option A adheres to the associativity law is going to depend on the proof that add here implements or adheres to the the associativity law. So of course, if we wanted to say, well, give us this function that can combine two A's into an A, along with an assertion that it is associative, that's exactly what a semigroup is. And so we can just change this to, we can leave it as add. We can change this type here to be semigroup A, and that's effectively how we started. All right, so this is the first example of actually using one of these type classes to abstract over addition in this case, or combining two values of type A. And just to show you that that works arbitrarily, for any monoid, like we saw this monoid here of maps. If we wrapped both sides in, let's say, an option, it should work just as well, given our definition. And here you can see we got back an option map string list int. And it's one value sum with the right union inside of it. And if we were to replace one of these inside maps with, let's say, a none, we get back the starting map alone. Right, so hopefully this example shows how with this organization of code, with using type classes to adhere to like the interface segregation principle and define just the bare minimal definitions of your polymorphic behavior, and then structuring the code such that we can get free instances of these type classes given other lawful instances, we can start putting together things that are very, very, very powerful, things that handle certain polymorphic behaviors much better than, let's say, like a traditional type hierarchy would handle, like an OO type hierarchy. So we're going to see more of, we'll see a lot more of semigroup and monoid coming up. Any questions at this point before we move on to foldable?
can this get a little confusing when you're working with types that aren't as simple as map and list? An example here is, right, if you have a map with the values as lists, it's easy to rationalize over this and say, like, well, lists, we know that the semigroup for list combines or appends, right? Versus like if there are just raw ints as values, the semigroup would do just straight addition on the values, I'm guessing, right?
I guess I'm not sure of the question. Sorry.
Okay, so maybe a better way to illustrate the question would be, what if you tried to use what if you tried to combine two maps where values were just int instead of list?
Oh yeah, sure. Well, a list of what? Like other you want other lists here?
No, that's what, no, I'm saying a map of string to just int.
Oh, gotcha. Like that? Whoops. Right. So the map monoid in this case would work the same way in that it's going to union the two maps together. And anytime you have a key conflict where both maps define the same key, it'll use a semigroup to combine that value. So here you can see like the A key has the value 4 because in this map it had the value 1 and it's combining that with 3. But then B and C are each brought over, unmodified because they were unique in each map.
So in both, I mean, I guess help me understand this, the proper terminology. You have in the above example, I thought you had an implicit semigroup for list, right?
For list of int, yeah.
Right. And here, it's just the semigroup for map that's helping do the addition.
No, it's semigroup of int.
Semigroup of int.
Yeah.
Okay.
So
this is, yeah. Sorry.
no, it's good. We didn't look at the definition of monoid for map, so let's do that. Here is the definition. I'm going to bring this down. And you can see it looks very similar, or at least it has some similarity to the option monoid. Right? It says that it can give you a monoid for any map of type KV if you give us a semigroup for V. And it's implemented very much like the option one. It happens, because maps, of course, can have more than one key in them, unlike options, which can only have one value in them. This has to handle like traversing through the two maps. It just does it with like a fold left. It's a little complicated, but effectively, it's just, this code here is just doing a map union, such that if it ever hits a conflict, it's going to use this semigroup to append the two values together. And that's why in like our second example, we were getting a semigroup of int, whereas in the first example, it was getting like a semigroup of this, list of int.
So you could pretty trivially write a semigroup. Like basically, one thing that would be easy to do is write a monoid for map or a monoid for an entry. So like you can add any element that is a monoid and like come up with a count of the entries. So I said that badly. But like let's say in this example, or in your first example, you wanted to find out every time you had overlapping values, which you don't actually have. But you could write a semigroup that takes two lists together and counts, like returns instead of just the combined list, returns the combined list plus a count of every time like a duplicate list was found. I'm going to paste an example after the talk of what I'm talking about.
Yeah.
But it just occurred to me.
Yeah, I think we're going to look at that next, actually, or at least we'll look at the function that enables that next. Any other questions on semigroups and monoids before we move on?
One more.
Sure.
Are there any data types off the top of your head that will be impossible to write a monoid for? I mean, I think you gave a similar example for, like, you
Sure.
can't write a monad or something like that.
Yeah, I mean, so do you mean like data types that have semigroup instances but don't have monoid instances?
Right.
Yeah. The simplest case, like we have our list monoid, right? Our list monoid, we said the combine operation is just appending. The equivalent of something like this. And we said our empty element for that was the empty list. So the simplest way that we can generate a data type that does not have a monoid instance for, does not have an identity element for its append operation would be by removing the identity element from the inhabited types of that, or inhabited values of that type, if that makes sense. So my point is that list where the append operation is really just concatenation has the zero element of the empty list. So we can just define a data type that's the non-empty list. It's a data type that never allows an empty list to exist. And that has a semigroup instance, but no monoid instance as a result. At least there's no monoid for the appending operation. And the simplest way to define a non-empty list would be like this, right? So this null data type, we could define a semigroup like so. And anyway, we wouldn't be able to define a monoid for that operation because it would require us people to generate a non-empty list for some value type A, and we explicitly prohibited empty lists from existing in this data type. What I like about the non-empty list example is that it shows a good technique of anytime you say, is there a data type that has an applicative but does not have a monad instance, or is there a functor that doesn't have an applicative instance? Anytime you do that, you can identify what characteristic that you're relying on to generate, the bigger instance, the monad instance or the applicative instance, and then just take it away. And sometimes doing that's a bit arbitrary, but sometimes doing that, like here in the case of non-empty list, ends up being an absolutely practical, useful data type. Like non-empty list is extremely useful, right? We use it a lot in validation, for example. And yet, the the question of can I define a monoid, or what's a list without its monoid instance, yields this data type. I think that's really neat.
Can you go over the parameters to semigroup instance that combine the A to A to A? What that signature is actually trying to say?
Back over here.
Yes.
So combine here is just defined as like a function 2, but where the second argument is by name. So like a good example, well, no, it's not. I mean, there are some semigroup definitions that never need to evaluate the right argument. We haven't actually seen any of those yet, although it's very trivial to define one that never needs to, I shouldn't say never, but in some cases doesn't need to look at the right argument. So we can sort of try to compensate for the fact that Scala has strict evaluation or strict parameters by defining like the second operation as a by name. But anyway, later when we want to actually define a function, or define like this instance method that takes our combined instance as a higher order function, we need syntax that lets us do that. So that's really all we're doing here is saying this is a function 2 of a strict A and a by name A. Even though it looks sort of like we're saying A to A to A, really all we're saying is like a function 2 with a by name in the second position.
I guess, so what is the benefit of writing that instance rather than just having clients override and create their own combine method? I mean, it looks like the same exact signature.
Yeah, it is completely the same exact signature. Oftentimes you'll see these instance methods on type classes just to reduce the boilerplate. So like a good example is monoid. Whoops. Like these monoids, right? Like each one of these would be probably 3 times longer.
Yeah.
The other nice thing here too is that like you can infer the types, right, of this function because of the 0 value. Oh, and you don't have to worry about the by name stuff, right? The by names, when defining it here without types, the by names don't show up in the syntax, even though technically like y is still a by name parameter. It still behaves like a by name parameter.
Right.
So it's just pure syntax. It is worth showing though that like we can define an option instance that takes advantage of that by name. So like a completely legal or law-abiding option monoid is monoid dot. Well, let's do it here. We'll just define this as an alternate monoid for option. We're not going to require a semigroup. We can just define it for all A. So this looks so far better. In that at least I'm claiming that we can define it for all A. It has less restrictions than this one up here, which requires a semigroup for our A parameter. So this seems like it's pure win. Now, in order to do this, the first 3 cases end up being okay. This last case is a little problematic, right? We can't say sum xx plus yy. We don't have any append operation here. Instead, what we could do is just say x or else y. So we could just take the first defined option. So if x is a sum, we're going to return it regardless of whether y is a sum or not. And in fact, with this definition, x or else y, we can get rid of all of these cases because each one of these cases yields the same result if you put it through this equation. So we could replace this whole definition of option with x or else y. I'm not going to spend the time to run it through the tests, but if we run it through the test, it will pass, right? Like I said, the first three cases end up being exactly the same, and we showed earlier that these all adhered to the identity laws, the two identity laws for Monoid. So all that's really left is associativity, and this X or else Y, since we're always picking the left side first, it ends up being associative. If we instead always picked the right side first, it would still be associative. So we can do either one. But anyway, you will see this at times. There are definitely times where you want to have this definition as your option monoid, even though this one is really what we'd expect. And so hence, like most libraries are going to define this one as the one that's available implicitly and provide some alternate way to get at this one, whether it's like here where you have to call it directly or whether you do something fancy. But there'd be some.
So what would the way to call that look like? If you just wanted to put that in scope, you'd have to like define your own implicit and then make it equal to that?
Yeah, right. You would do like, oh no, what did I break? Definitely shouldn't have exited out of our REPL. Let's just do add x, y. Sorry, add xx, yy.
You're not continuously compiling right now.
I know, I was doing it by hand.
No, I just didn't know if you were looking at stale errors.
Oh, gotcha. Yeah, so like now you would say we would call it, what do we call it? Option monoid alternate. Actually, so before we do that, let's just say like sum1 plus sum2. Oh boy. We'll do the same thing with options. All right, so we get sum3, and now if we did that same example after defining this implicit val, oh, sorry. All right, there's our example using the implicit definition. Now we'll bring in our monoid here and do it again, and we get sum1. I'm planning on adding a macro at some point soon to structures where you could type instead this. The idea is this local macro. You'd be able to do it like this. And so all it does, it would take var args here, and everything you pass to the var args would be defined as an implicit val in the block that follows. These are like local instances of a type class is the idea, but it's not there yet.
That's nice. Keeps your implicits in the right scope.
Yeah. So that was an example of a monoid instance for option or option A that doesn't actually need to evaluate the right parameter. Right? Like when we passed sum in on the left side, it never needs to evaluate this right side. And if all of the macros are working correctly, we should be able to prove that by saying something like this, right? And you can see that this right-hand side never got evaluated because of the by name. Whereas if we did the same example, but we put a none on the left-hand side, and we gave it the right type, now you'll see the print line come out. So anyway, that's a motivating example for why you define the right side as by name. All right, so we're going to start the foldable type class. We're only going to spend about 4 or 5 minutes on it, and then we'll do the bulk of foldable this Friday. But I do want to give at least 1 or 2 examples of the foldable type class. So let's take a look at it. Foldable is going to be our first type class that we've looked at that really doesn't have any laws. So rather than calling it a type class, it's it's still a type class, but the idea is that it really is only abstracting over this ability to fold. It's pure ad hoc polymorphism. We want to be able to talk about all of the different types that have this folding notion. So we're going to define it in 2 ways. We'll define 2 functions, fold left and fold right. And then we're going to define a bunch of derivative functions from that. There are a couple other ways to define this type class. So another way to define it is that our only abstract operation would be fold map. Actually, I'll just take the signature. So there's a way to define it like this. So here's our fold map definition. The idea is that we would start with like an f of a, and we have a function from a to b, but we require a monoid for our b element. And we'll give back a b at the end. It turns out if you define this as the only abstract operation, you can derive fold left and fold right from this operation. And then there's another alternate definition of this where the only abstract operation is like toStream, which says given an f of a, return a stream of a. And really no one ever implements it this way, right? I'd be very surprised if we ever saw like a production quality foldable type class that chose to make toStream the one and only one abstract operation. But it's very important to keep this in mind that everything that Foldable is doing can also be done with this signature. You pay this overhead of creating a stream and then applying operations to the stream, but that's really all we're capturing here is that our container has the ability to be converted to a stream. So anyway, our definition, we chose to let fold left and fold right be our abstract operations. And these are going to have signatures that are very familiar from like the Scala collections framework. So we'll start with like an f of a and some initial b value. And then we have a function, a function to ba, to a b, it returns a b. So this is very much just like fold left on, let's say, list. We define both fold left and fold right abstract. Again, because of Scala's behavior or strictness in parameter passing, some data types might have better definitions for like fold left and fold right built directly into them, and we want to be able to encourage implementers to implement it in the right way, or implement it in a performant way. So rather than say like we're going to define fold right as the only abstract operation, and then define fold left in terms of fold right, which you certainly can do. That's what Scala Z chose to do. By doing so, you get a very non-performant fold left derived from most data types. And if most of your foldable things are going to end up being collections anyway, you really want to encourage the implementers to use like the native collections fold left method, since it'll be very much optimized. Let's just do a couple examples, and we'll look at this type class a lot more next time. So here we have a list of options, right? A list of option int. I wonder if I can do this. Let's do it a slightly different way. I'm going to ask for a foldable instance for, that's not nice either. Well, let's use fold map, I guess. So with fold map, we're going to be passed some option value. I'll call this O. And we have to convert this option value to something that has a monoid. Now we know that option int has a monoid because we used it in the previous examples. So we can just return O as our output. So we're going to fold map with our identity function. And then you can see in this case, we're getting sum1 as our result. This was the first value here that succeeded. And the reason we got this answer is because we changed the monoid int definition in scope in the previous section. If we were to restart our REPL without that bad definition in scope, we would get the sum of all the individual values. It turns out like list defines this fold, or list has a fold method on it directly, but the idea of fold map with an identity function shows up pretty common. And in structures we call that fold, but I can't get access to it because it has the same name as fold on traversable ones. We could address that by adding like a alias for fold here. I don't know what we would call it. For now, let's just say like ffold. And now you can see if we call it ffold, we get the result. And so like this works for any possible monoid. So for example, if we wanted to count the number of elements in our list, again, let's assume list doesn't have like a size method. Perhaps we're doing this in a generic function that's polymorphic over the data type. So hence all we have is like a foldable. We could calculate a size by running fold map and converting each individual entry into the number 1. So if we convert each entry into the constant value 1, that's just an integer. Integers have monoids, and hence we'll get 1 plus 1 plus 1 is 3, and this ends up just being the size operation. And so anyway, next time we'll look at the foldable type class in detail, and we'll see how to implement some of these operations. But it's the interesting thing about foldable so far is that you can see how we're using monoids in a way to implement some pretty routine operations. And yet, these operations are like completely general in the sense that like if you had like a big nasty list of maps, you could union them all together, unioning all duplicate keys with a fold map.